All right. Hello, everybody, and welcome. Today, we are going to be starting off the first topic from number and algebra, which is sequences and series. I'm not going to finish the entire topic in this video, but I will be doing as much as I possibly can. Okay, so first of all, we need to start off by sequence, yeah? By what a sequence is, what the definition is, yeah? So a sequence is an ordered list of numbers, yeah, terms in a definite order. There we go. So this is the first thing that we need to discuss. A sequence is an ordered list of numbers, terms in a definite order. Okay. So an example for this could be, for example, 2, 5, 13, 5 again, -4. So over here, I have a list of numbers that is just ordered, that are ordered in a specific way. The negative doesn't come before the negative, but before the 2, yeah? And the 13 doesn't come after the 5. It's ordered this way, yeah? So that's why it's a sequence, okay? But when we're studying sequences, generally there is some sort of pattern that we can analyze or see in the sequence. For example, here in this one, we have 2, 4, 6, 8, 10. Yeah. So the pattern in this sequence is that what we have even numbers, right? Or for this sequence right here, 1, 3, 5, 7, 9 right? Here we know that the sequence or the pattern that this sequence is following is that it's all odd numbers. Here it's all even numbers. Yeah? So that's that. Let's clean this up a little bit. Yeah. Okay. So now that we have that in mind, when I'm talking about a sequence or when we have a sequence, let's say for example 2, 4, 8, 16, and 32. This is a sequence of powers of 2. Yeah. So let's say I have this sequence over here, okay? And I just want to mention the fourth term. I want to talk about um, 16 specifically, okay, in the question. I want to mention it or something. What am I supposed to call it? Am I supposed to say, well, the fourth term, yeah, is equal to 16? No. Okay, I cannot do that, obviously, and it takes too much time to write all of this and so on. So we need to denote it. And luckily we have a notation for it. So it's going to be UN. Yeah. So this is the basically describes the nth term. So where in the sequence is that specific number, position-wise? Yeah. So here, for example, n, sorry. So here, for example, n is equal 1. Okay. Here, n is equal 2, and so on. So that means that if I want to talk about 16, it's the fourth term. So I denote it by U4. So U4 is equal to 16. Yeah. So I'm saying that, or by this, I'm saying that U4, the fourth term of this specific sequence, is 16. Okay? So that's how we denote it. Okay, let's move on to the definition of a series. Okay, so if let's say a question asks you to describe a sequence or to give a general formula to a sequence, you need to be able to do that, using math terms and not really, write like the sequence are multiples of 2. Yeah, so if let's say this is my sequence, right? 2, 4, 6, 8, and then it goes on. These are multiples of 2, right? So you're multiplying, this is 2 times 1, 2 times 2, 2 times 3, 2 times 4. Okay. So there's generally two methods of describing a sequence. First of all is when you're describing the general form or the general term un in terms of n. Okay? So what do I mean by in terms of n? In terms of n basically means that you are you have n as an input. It's a direct input to describe the sequence. So for example, in this case, it's 2n, right? Because when n is 1, yeah, u1, then 2 is multiplied by 1, which gives us 2, right? When we're trying to find the second term, u2, 2 times 2, which is equal to 4. Want to find the third term, 2 times 3, equal to 6, and so on. Yeah? So the first way is a general form to describe it where n, in terms of n, we describe it in terms of n, where n is incorporated or it's an input in the formula. Now, the second way to describe it is something called the recursive formula or the recursive relation. So recursive relation. Okay, so recursive relation. So the recursive relation uses two things. It uses u1, your first term, and it uses un plus 1. Okay, so you need to have u1, yeah, in order for this, for the recursive relation to work, okay? So let's explain it by an example. Let's say that u1 is equal to 10, yeah, and then un plus 1, yeah, is equal to un plus 2. Okay, so what does this mean? The recursive relation basically, so this un plus 1 is describing the term after the one, let's say, for example, that you already have. So if I have u1, then un plus 1 is equal to u2, right? So to get to the term afterwards, you need to do this. Yeah? So the recursive relation basically is just describing what is happening to the first term that I'm looking at and how we got to the second one. So if I have u1 is equal to 10 and the recursive relation un plus 1 is equal to un plus 2, right? Then that means that in order for me to get u2, I have to say u1 plus 2, which is what? 10 plus 2, which is 12. Look, un plus 1. The reason that we describe it this way, or that we describe the terms this way, is because we need to find out what n is to plug it into whatever like sequence we have. Yeah? So un, yeah, plus 1. If I want to find my second term, right, I need to think, okay, well, what term plus 1 is going to give me 2? It's going to be 1, right? So then I'm plugging 1 for n. So in this case, n is equal to 1. Sorry, not up here. In this case, n is equal to 1, which is why I said u2, because it's u plus 1 plus 1 is equal to u1 plus 2, right? U1 is already given to us. This is why I said that U1 has to be given to us in order for us to actually, build this sequence. So U1 is, in this case, 10. Add 2 is 12. Look, let's do, for example, U3. U3, right? So let's use this formula. Wait. Un plus 1 is equal to un plus 2. Okay, so what number does n have to be for me to have, what number does n have to be so that when I add 1 to it, it's equal to 3? It has to be 2, right? So it's going to be u2 plus 1 is equal to u2 plus 2, right? So u2 plus 1 is u3. And u2 is already given to us as 12 plus 2. It's not given to us. We worked it out. We worked it out. So therefore, u3 is simply 14, right? Let's do u4. If I have un plus 1 is equal to un plus 2, what do I have? What does n have to be so that when I add 1 to it, it equals to 4? It has to be 3, right? So it has to be u3 plus 1 is equal to u3 plus 2, right? u3 plus 1 is u4. u3 is equal to 14, we just worked it out, plus 2, which is equal to 16. So u4 is 16, u3 is 14, and u2 is 12, and u1 is already given to us, which is 10, right? So the sequence that we have so far is 10, 12, 14, 16, dot, 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 because it keeps on going. There we go. So that's the recursive relation. Yeah, it's that we always use this un plus 1, and then you say un and you say what is happening to un. So I'm always adding 2. You can also, for example, say that un plus 1, right? This is always fixed. This term is always there. But you can always say that, for example, what is happening to un? You can say that un is being multiplied by 2 minus 3, and then all of that is squared. This could be the pattern that is emerging. Yeah. So you always say un plus 1 because that helps you find or helps you include the term that you already have into your formula. It allows you to incorporate u1 so that you can actually come up with a solution. Yeah. So if you're given u1, like let's say it's 3 in this case, then that means I can work out for u2. It's perfect. Or if let's say, yeah, yeah, it's perfect. So that would be what? U2 plus, sorry, it's 1 plus 1. So it would be u1 plus 1 is equal to 2 times u1 minus 3 all squared, right? Now, what does that mean? This is u2. We're working out for the second term. So 2 times u1. u1 is 3 minus 3, and then all of that squared. 2 times 3 is 6. 6 minus 3 is 3. 3 squared is 9. So u2 is equal to 9. And then u3 will follow that pattern. So the recursive relation is basically you taking this fixed form, un plus 1, and then equating it and saying what is happening to your terms. What is happening? Are you multiplying it by 2? Are you squaring it? Are you subtracting from it? Are you adding something to it? Whatever. Yeah? And that is the recursive relation. Okay, so now let's move on to the first sort of bigger topic, which is arithmetic sequences. It's a type of sequence. Let's look at what it is. Okay, so now let's go ahead and start or talk about arithmetic sequence. By the way, sometimes for short, I'm just going to say a point s point. Yeah, like this basically just says arithmetic sequence. It's just for short. So, okay. So an arithmetic sequence, I'm going to start with an example rather than trying to explain what it is. So because it will be easier to understand with an example first. So let's say we have this sequence over here, 5, 8, 11, 14, 17. Okay. So in this sequence, let's try to notice what the pattern is. What is the pattern between all of these numbers? What is happening to these numbers as we move forward, right? So here, for example, we notice that 5 to 8, that's 3, right? So in order to move from 5 to 8, that's 3 points. Then it's the same thing from 8 to 11, 8 to 11 to 14, 14 to 17, right? So each and every time we move from one term to the next, we're adding 3, right? We're always adding 3. And that's basically what is an arithmetic sequence. An arithmetic sequence has terms that are listed in an order, and there's always an exact difference between each term. Like there's a what we call the common difference. Common difference. So the common difference is denoted by D, yeah? So this is the basically the difference between each every term, and it's constant. It's always there. It's not like, for example, I can add 3 to this term and then add it to that term, and then the next one I can change it to plus 4. Then it's not an arithmetic sequence. An arithmetic sequence always has the common difference 3 between every single term. Okay? So, in an arithmetic sequence, we always want two things. You always want to try to look for two things or make sure that you know two things. You always want to know the first term u1, and you also need to know the common difference. If you know these two, you're good to go. Yeah, you're good to go to solve for whatever other information that the question is asking you to find. Okay, so let's take an example. If let's say u1, if u1 is equal to 1 and d is equal to 2, then the arithmetic sequence that we get from this one is what? We have 1 as our first term, then we add 2, so 3, and then 5, and then 7, and then 9, and then 11, and then 13, and so on and so forth. So it keeps going, right? Let's say, for example, if u1 is equal to negative 10 and d is equal to 5, right? Then we start with negative 10, then it becomes negative 5, then it's 0, and then it's 5, and then it's 10, and so on, right? There we go. Now notice, let's say you can have u1 is equal to 10, and d can also be negative. So you can actually start so your common difference can actually be in negative, so you're moving like into the negative direction, yeah? So you can start with 10, and then you can go to 5, and then 0, and then negative 5, and then negative 10, and so on into negative infinity, yeah? So that's that. So there we go. We have those ones. So now, in when we were talking about sequences generally before, we had two ways to describe a sequence. We had it when we were using when we're describing un, the general term un in terms of n, and we also had what we called the recursive relation, right? Well, for this one, there's an actual set formula. This is given in the formula booklet, so you don't have to memorize it, but when you use it so much, you probably will. So un is equal to u1 plus n minus 1 times d, okay? Okay, so it's important to see why we use the formula this way. Why is it built this way? So first of all, un, this is the nth term that we're trying to just find generally, yeah? Now the reason I said earlier that you always need u1 is because this is what you're going to need for a formula like this, yeah? Now let's say you want to find u5, okay? We're trying to find u5. We don't know what it is and we need to find it. You're going to start at u1, yeah? This is the first point that you have. Let's say you're given u1, yeah? Now, to get to u5, you need to do what? You need to move one common difference, right? So this is a common difference d. So that's u2. Then you move again, right? You now are at the third term, again common difference. It's going to be here, right? And then you're going to move one more time, so it's going to be u4. You know u4, again common difference. And then finally, you're going to get to u5, another common difference. So let's see. So you started at u1, you had 1, 2, 3, 4. So there's in total, right? In order to go from u1 to u5, you um, added the common difference four times, or you multiplied by the common difference 4 times, right? So look at this here. If I were to plug in u5 for my formula over here, it would be u5 is equal to u1 plus 5 minus 1 times d, which equals to u1 times plus 4. Let me rewrite this here. u1 plus 4d. Yeah? So you're starting at the first term and you're adding 4 times the common difference to reach to u5. Yeah? So this is why we use this formula. It's generally, this is how you can break it down and understand it. Okay, so let's move on and let's do an example. Okay, so in this question, we're given u1 and we're given d. So u1 is 3 and d is equal to 5. So this question is being really nice to us because we have the terms that we need. So we need to find the first 4 terms. Well, okay, the first 4 terms we can simply do with ourselves. So since u1 is 3, we can just start with 3 and then add 5. So add 5, that's 8. And then add 5, that's 13. And then add another 5, that's 18, right? So these are the first 4 terms, 3, 8, 13, 18. Yeah, cool. Now, we need to find now the 100th term. So for this one, of course, in order to, keep on going to the 100th term, it's going to take a long time. So instead, we're going to use our formula. Un is equal to u1 plus n minus 1 times d. Okay, so let's see what information we have. We want to find u100, okay? u1 is 3 plus 100 minus 1 times d, which is what? 5, right? So u100 is going to equal to 3 plus 99 times 5. Yeah. And this is going to equal to 498. Yeah. So our 100th term of this sequence is 498. So what did we do here? We started at our first term, which was 3, right? We started at 3. And then we added the added 99 times the common difference in order to get to the 100th term, yeah, which is equal to 498. Okay, cool. So that's that. Now, let's take a question where we are not given the common difference. So let's say u1 is equal to 100, and we have that u16 is equal to 145. Okay, so what are we going to do in this case? Well, let's build our formula. So we have un is equal to u1 plus n minus 1 times d. Okay, so we have this. Now, we know u1 is 100, and we know that u16 is equal to 145. So what we're going to do is we're going to use this information. We're going to plug this value into our formula in order to find d, right? Because if we plug in this value, we know that what the nth term is. We're going to know what n is, yeah, n minus 1, what is it going to be? And we already have u1. So then the only unknown variable in this case is going to be d, which we can then solve for if we have all the other variables. Yeah. So un, we're going to replace that by u16 is equal to u1, which is 100, plus n minus 1, sorry, I shouldn't be writing n, it's 16 minus 1, yeah, so 15 multiplied by d, right? So 100 plus 15d. And we know that u16 is given up here, it's 145, so we're going to say 145, right? So when you solve for this, d is going to equal to 3, okay? So it's as simple as that. So then now we have found D, and it's also asking us to find U7. So if you have D, then finding U7 should be easy peasy. U1 is 100 plus 7 minus 1 multiplied by 3, right? So that is going to then give us 118, right? So you're going to have 100 plus 6 times 3, yeah? And that's 118. Okay, cool. So that's that. Now, again, just as a final reminder, for an arithmetic sequence, yeah, make sure that you know U1 and D, yeah? These two values are probably the most important because they are what help us build this formula, yeah? UN plus n minus 1 times D, yeah? If you have this formula, if you have the variables that are needed for this formula, then you are good to go, yeah? Because whatever term you're trying to find UN, you're going to have n for, and that's that. Okay, now let's move on to the sum of an arithmetic sequence. Okay, so the sum of an arithmetic sequence. Now, the sum of an arithmetic sequence basically means that, let's say I have the arithmetic sequence 3, 4, 5, 6, 7. Really basic. The sum of arithmetic sequence basically then means that I'm just replacing my commas with addition signs, right? So all of that added onto each other. I made a mistake here. There should be plus. So 5 plus 6 plus 7 and so on. Yeah? So there we go. So we have that down. So now there are two general formulas that we can use to find the sum of an arithmetic sequence. Now the first one is denoted by Sn, and it's n divided by 2 multiplied by u1 plus un. Okay? So this is formula number 1. For formula number 2, it's also denoted by Sn. You say n divided by 2 multiplied by 2 times u1 plus n minus 1 times d. So we see that there's a little similarity to the formula for the general nth term of an arithmetic sequence. Okay, so it's important to know for formula number 1, the elements that you need are u1 and un. Yeah, so your first term and your general term. Then for formula number 2, what you need to know or what you need to have is u1 and d. Yeah, so just keep that in mind. u1 and d, then you use formula 2. u1 and un, use formula 1. Yeah, and if you have u1 and un, then that means that, this formula, in my opinion, is of course easier. Yeah, it's a lot shorter than this one. Okay, cool. So let's move on and let's do an example. So let's say we have an arithmetic sequence 3, 5, 7, 9, 11. Okay, so we're supposed to find sorry, this keeps on going infinitely. Yeah. Now we're supposed to find S3. So S3 is pretty simple, right? It means that we're going to add the first 3 terms of the arithmetic sequence. So we're going to be adding 3 plus 5 plus 7, right? So S3 is therefore 15. Okay. Now, what about finding S101? Because this sequence keeps on going, right? This sequence keeps on going to positive infinity. So what are we going to do? What information do we have? Do we have un? We do not have un, right? Because this just keeps on infinitely going. So that means that we'll have u1, right? Which is already clear, it's 3. And we're going to have the common difference. And we can work the common difference out just by looking at the sequence. So 3 to 5, you're adding 2. 5 to 7, you're adding 2. 7 to 9, you're adding 2. So the common difference is 2, right? So we're going to use our second formula. Our second formula is n over 2. So 101 over 2, excuse me. 101 over 2 multiplied by 2 times 3 minus, sorry, plus 101 minus 1 times d, the common difference 2, right? So to simplify this, we're going to keep 101 over 2 as it is. Now, this is going to be 6 plus 101 minus 1 is 200 times 2 is 200. Yeah? 100 minus 1 is 100. 100 times 2 is 200. Right? So you're going to have 200 plus 6. So that equals to 101 over 2 multiplied by 200. And that's 2006. 206. Right? So that is going to give you 10,403. So the sum of the first 100 terms of this arithmetic sequence is 10,403. Okay, good. Now let's move on to another question. I find this one pretty interesting. It's a show that question. So we're supposed to show that 1 plus 2 plus 3 plus dot 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 plus n is equal to n times n plus 1 divided by 2. So we're supposed to show that this arithmetic sequence, yeah, is equal to this formula over here. Okay? So let's look into how we're supposed to do that. So first of all, let's look at the elements that we have from this arithmetic sequence. We have u1, and we have the nth term, and we also have the common difference. It's pretty easy. It's 1, right? So u1 is equal to 1, common difference is 1, and the un is n. Okay? So since we have u1 and un, I think everyone would rather use the easier formula, right? So we're going to use formula number 1. So Sn is equal to n over 2. It's your, sorry, 100, wait 1 second. Sn, yeah, is equal to n over 2, yeah, multiplied by u1 plus n, right? And simply just simplifying this, yeah, this multiplied by that is just going to give you n times 1 plus n divided by 2. Yeah, so simply using the formula, we'll get the same exact result, right? These are equal to each other. Okay, good. So that's that. Now moving on. Yeah, we'll do an interesting question or a question that will help us understand it a little bit more. So the question states, right, that the third term of an arithmetic sequence is 0. Yeah, so arithmetic sequence, your third term is equal to 0. So u3 is equal to 0. While the sum of the first 15 terms is negative 300. So sum of 15 is equal to negative 300. Okay, so this is the information that we're given. What are we supposed to find? We are supposed to find the first term and the sum of the first 10 terms. So we're supposed to find u1, we don't know what that is, and the sum of the first 10 terms. Okay, cool. So we're given u3 is equal to 0, s15 is equal to negative 300. Okay, now let's set up these. Now, these obviously, when you're using your equations or when we use our equations, these are two different equations. Like to find the a certain like nth term, yeah. Sorry, my headphones cut out. So to find a certain nth term, un, you will have to use this formula, right? u1 plus n minus 1 times d, right? And to find a certain sum, right, you need to say Sn is equal to n divided by 2 all times 2 times u1 plus n minus 1 times d, right? So these are the two formulas that we should be using. Okay, so we'll simply take the information that we have over here and plug it into these two formulas, okay? So let's see. U3, so it's going to be U3 is equal to U1 plus n minus 1, so 3 minus 1, 3 minus 1 times d, right? We know that U3 is 0, so this is going to be equal to 0 plus, equal to U1 plus 2d, right? There we go. So this is our first formula that we have. Now let's move on to the second one. What about S15? So S15 is equal to 15 divided by 2, all multiplied by 2u1 minus 15 plus, 15 minus 1 times d, right? So this will give us what? 15 over 2 divided multiplied by 2u1 plus 14d. Now we need to expand this information or expand this fraction by the bracket, right? So we'll keep it as it is. So we'll say 15 over 2 multiplied by 2u1. What is this going to equal to? Well, these two 2's cancel out, so it's going to be 15u1. Yeah? So 15u1 plus, and then we'll multiply 15 over 2 by 14d. So 15 over 2 multiplied by 14d. Yeah? So 15 times 14 is going to be 105 is going to be 105d because 15 times 14 gives us 210, and that's divided by 2. Yeah, so 210d divided by 2, which is 105d. So this will be 105d. So, and S15 is given to us, and it says that it's negative 300. Okay, so this is our second formula. Okay, sorry, it's a bit messy right now. All right, so we'll take these two formulas and we'll put them into a system of equations. So u1 plus 2d is equal to 0. And 15u1 plus 105d is equal to negative 300. This will give us that u1 is equal to 8 and that d is equal to negative 4. You can do GDSC for this, or simply just solve it yourself by maybe multiplying this equation by 15 so that you have 15u1, and then subtracting both equations to cancel u1, and then finding d, and then plugging it into equation number 1 again to find u1. Okay, so u1 is equal to 8 and d is equal to negative 4. So we know now u1, this is the first part of our question. Now we need to know what the sum of the first 10 terms is. So we're going to simply use our equation. So 10 over 2 multiplied by 2 times u1, which is 8, plus n minus 1, which is 10 minus 1, times d, right? Sorry, times negative 4, because we have d. Negative 4. Okay, so that simply, all of that will give us negative 100. So the sum of the first 10 terms is negative 100, and therefore we have solved the question. Now, before we move on to our second type of sequence, which is geometric sequences, we need to discuss something for consecutive terms. Okay, so what I mean by consecutive terms is, imagine in a sequence, let's say you have 2, 4, in an arithmetic sequence, you have 2, 4, 6, 8, 10, and then it keeps on going. Okay, imagine I take these three. Okay, or for example, these three, 6, 8, and 10. So in this case, or like when I'm saying consecutive terms, I mean terms that follow each other in a sequence. No matter where they are in the sequence, they're following each other. Okay, so I'm going to model this by saying A, X, and B. Okay, so these three terms are always following each other. So they're terms that are directly after each other. They follow consecutively. Yeah. So for terms that follow each other consecutively like this, we can find, or we can deduce two things. First of all, the term that leads after another one, if you subtract this term, for example, by that one, you will get the common difference. So if x minus a is going to give you the common difference. Same thing applies for this term and that term, right? So if you subtract b from x, yeah, you will get the common difference. So if you subtract the term, the term that is larger than the one before it, or the term minus the term before it, then you will get the common difference. Okay, so that's the first thing that we need to deduce, or we needed to deduce. And now the second thing is the mean. Yeah, if you have three consecutive terms here, then the term in the middle, okay, is equal to the term before and after added to each other, so a plus b divided by 2. Okay, so the term in the middle is the mean of the term before and after. Okay, so let's say an example. Let's say the 2, 4, 6, 8, 10. Yeah, let's say I take these ones. Yeah, these three terms are following each other consecutively. Yeah, it doesn't matter where they are in the sequence, they're just following each other. That's all I care about. Yeah, so to find the common difference, first of all, so you can do 4 minus 2 and you're gonna get 2, or you can do 6 minus 4 and you're also going to get 2. Yeah, so this is what the common difference. Now for the mean, let's take 4 is equal to 2 plus 6 divided by 2, right? So you can already see that's going to be 8 divided by 2, which is equal to 4, therefore true, right? Let's look at a different example. Let's say 1 plus 3 plus 5 plus 7 plus 9 plus 11. Why am I saying plus? Excuse me. 1, 3, 5, 7, 9, 11, and it keeps going. Let's take these three terms right here. So, first of all, if I do 9 minus 7, I'm going to get what? I'm going to get 2. If I do 11 minus 9, I'm going to get 2. Yeah? So that's for the three consecutive terms. Now, if I take the mean, yeah, of these three terms, it's going to be what? 9 equals 7 plus 11 divided by 2. So 7 plus 11 is what? 18. So 9 is equal to 18 divided by 2, which is equal to 9, which is also true. Yeah, applies the same for these three consecutive terms. If I say 3 minus 1, I'm going to get what? 2. If I get 5 minus 3, then I'm going to get what? 2. Okay? If I find the mean, 3 is equal to 5 plus 1 divided by 2. Again, 6 divided by 2, which is equal to 3, which is true. So that's that. Okay, let's move on to geometric sequences. Okay, so now we're going to move on and we're going to discuss geometric sequences. All right. So, like I explained arithmetic sequences, I'm going to go ahead and explain geometric sequences the same way, okay? So let's imagine that I have this sequence right here, 5, 10, 20, 40, 80, and then it keeps on going, yeah? Now, I'll ask you what you see here, or what, from one term to another, what is happening to this term, for example, for it to go to 10? What's happening to that term for it to go to 20, 20 to 40, 40 to 80? Here we see that these terms are being multiplied by 2. Okay, so we are multiplying by 2 every single time to get the next term. So this one will also multiply by 2 to get the next term, and so on. Okay, so in arithmetic sequences, we said that, let's say, for example, we have 2, 4, 6, 8, and then it keeps going. Here we're adding 2 each single time, right? We're adding 2, adding 2, adding 2, right? Here we're multiplying by 2. So arithmetic sequences deal with addition and subtraction, while geometric sequences deal with multiplication and division. Yeah, that's not a good division sign, sorry. And division, okay? So that's that. So over here in the sequence, we multiply each number or each term by what we call the common ratio. In arithmetic sequences, we say it's common difference and it's denoted by D. In geometric sequences, we say that it's called the common ratio and it's denoted by R. Okay, so the common ratio, so these terms are all multiplied by the common ratio R equals 2, right? So we're multiplying by R equals 2 every single time. Okay, so like arithmetic sequences, the important terms that we need to look out for or always try to have are U1 and R. Yeah, so we need to have U1, the first term, and R, which is the common ratio. Okay, because with those two, you can build your entire sequence using a formula. But before we get into the formula, let's talk about some examples. Let's look at some examples. So I'll use red for this one. So let's say U1 is 1 and your common ratio is 2. Okay, so then when you start building your sequence, it will look something like this. You have 1 multiplied by 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, and you keep going. Yeah? For example, you can have something like U1 is 1 and R is equal to -2. Then in this case, you're going to have what? 1, and then you're going to multiply by -2 is -2. -2 times -2 is +4. +4 times -2 is -8. -8 times -2 is going to be +16. Sorry, +16. And then again, it's going to be -32. So here's the interesting part. In arithmetic sequences, when d is negative, like 2 for example, you keep on descending, 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 and you go into negative infinity. negative infinity, right? That's for arithmetic sequences. But geometric sequences, it's a bit different because when r is a negative like number, let's say negative a, for example, then your terms alternate, yeah? This term is positive, then the next one is negative, then the next one is positive, then the next one is negative, then it's positive, then it's negative, then it's positive, and so on. Okay? So that's the difference, yeah? In geometric sequences, if your common ratio is negative, then your terms are going to be alternating. Now, of course, you can have u1 is equal to negative 2, and then r is equal to negative 1, for example. Then, of course, you're going to be alternating. You're going to start with a negative number, but then you're going to go to a positive one. So negative 2 times negative 1 is 2, and then 2 times negative 1 is negative 2. And yeah, this is a really dumb sequence, but yeah. So that's that. Yeah. So now, R, however, yeah, or sorry, the common ratio can be between negative 1 and 1. Okay, so the common ratio can, for example, be half. Yeah, this is between negative 1 and 1. Now, when the common ratio is like this, yeah, and we're multiplying our numbers, so let's say if I have u1 is equal to 1 and r is equal to half, okay, then my sequence will be something like this: 1, half, a quarter, 1/8, 1/16, 132, and then keeps going, right? So when you have an r that is greater than negative 1 but less than 1, yeah, so it's in between these two, 1 and negative 1, then your r will always, like your sequence is always going to be approaching 0. Yeah, so that's not a great way to draw it. Approaching 0. Okay? So if r is greater than negative 1, but less than 1, so it's between negative 1 and 1, then your sequence is going to infinitely reach 0, or approach 0, not reach 0, sorry. It's going to infinitely approach 0. Okay? So that's something that's very important to keep in mind. Cool. So let's move on. So for arithmetic sequences, we saw that our formula was something like this: un is equal to u1 plus n minus 1 times d, right? And I discussed with you guys like why it's built like this. We have u1, and then you have a common difference, then you reach u2, and another common difference, and u3, and so on, right? So we're going to build a similar formula here for geometric sequences, or we're going to use a similar formula. So it's going to be un is equal to u1 multiplied by r to the power of n minus 1. Okay, well, let's see why that is. Let's say I start with u1, okay? And this is my first point. And then I want to go to what? u2, right? So I'll say u2. And then another one, u3. And then another one, u4. Okay, so let's say I have these 4 examples, right? I go from u1 to u4. So to go from u1 to u2, I have to multiply by the common ratio. From u2 to u3, again, multiply by the common ratio. u3 to u4, I multiply again by the common ratio, and now I'm at u4. Which means what? If I want to find, if I want to find the term u4, then I start at u1 and multiply it by r4 minus 1, which is what? u1 multiplied by r power of 3, right? So here, because I multiplied by r 3 times, if you multiply something by itself a couple of times or however many times, you can raise it to the power of, right? So r times r times r is r cubed, yeah? So we multiply u1 by r cubed to get to the 4th term of the sequence. Okay, so this is why we use this formula, or why this formula is great to use or utilize. Yeah. So let's say, for example, let's have an example, like try out a question. Okay, so in a geometric sequence, we have, or it's given to us that u1 is equal to 3, and that r is equal to 2. They are asking us to find the first 4 terms, so u1, u2, u3, and u4. And then the second one is the 100th term, so u100. Okay, so let's look at how we're going to do that. Well, for the first one, this one right here, we can just simply, just write 3, and then multiply by 2. So 3 times 2 is 6, then multiply by 2 is 12, then another one, 24. So those are the first 4 terms of the sequence. Yeah, that's question number 1 done. Now for u100, we're going to write it like this, is equal to u1, which is 3, multiplied by r to the power of n minus 1. So 100 minus 1, which is 99, right? We have the common ratio, sorry, so it's 2. 2 to the power of 99. Now, of course, that's going to be a very big number, so we're just going to leave the answer like this because we don't want to deal with writing all of that. Okay, good. So I'm going to go into a question which is slightly more difficult, okay? And we'll just break it down slowly together. Okay, so a geometric sequence has a fifth term of 3. So we know that u5 is equal to 3. Okay, and the seventh term of 0.5. So we know that u7 is equal to 0.75. 0.5, I said 0.5, right? So 0.75, sorry. The first term u1 and the common ratio is what we're supposed to find. So we don't know u1, we don't know the common ratio, which is very, very sad because u1 and the common ratio are the crucial elements needed in order for us to, just have a smooth sail, so to say. But we don't have those and we need to find them. So why did I keep? Yeah. Okay, and then we also need to find the 10th term. So u10 is equal to that. So of course, in order to find the 10th term, we need to know u1 and the common ratio. So we're going to find the common ratio in u1 first and then move on to find u10. Okay, so we know that u5 is equal to 3 and that u7 is equal to 0.75, right? So let's build our formula. Our formula is un is equal to u1 multiplied by r to the power of n minus 1, right? So I want to plug in these two values in for this equation, okay? So I'll do that right now. So u5, okay, is equal to u1 multiplied by 5 minus 1 is 4. So there we go. This is u5. So this is also 3 is equal to u1 multiplied by r power of 4. Okay, so we have that. This is our first equation. Now, the second one is u7. Let's plug in for that information. So you have u7 is equal to u1 multiplied by r to the power of n minus 1. So 7 minus 1, which is 6. u7 is 0.75. So 0.75 is equal to u1 multiplied by r power of 6. Okay, good. So that's our second equation. So now, what are we going to do? Well, we can divide both of these equations by each other. Yeah, so we'll divide both of them by each other. So what are we going to do? We're going to say, we're actually going to use the same terms. Or should we? No, sorry. We're going to say 0.75 divided by 3 is equal to u1 times r power of 4 divided by u1 times r power of 6. Okay? Actually, did I mix those? Sorry, I wrote that incorrectly. No. So it's 3 is equal to um 0.75 is equal to u times r power of 6 divided by 3 is equal to u times u1 times r power of 4. Okay, good. So now 0.75 divided by 3, we're going to leave that calculation for a second, And now u1 and u1 cancel out, and then r6 divided by r4 is going to give us r squared, right? So what is 0.75 divided by 3? That is 0.25. So 0.25. And r is still squared. So we're going to square root both sides. We're going to get r is equal to plus or minus 0.5. Okay? So plus minus 0.5. Okay, so this is our common ratio. So our common ratio is two values, yeah, plus positive 0.5 and negative 0.5. Okay, so what we are going to do now is take this r and plug it into our formula over here. Yeah, so 3 is equal to u1, da 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 da. So 3 is equal to u1 multiplied by the common ratio 0.5 to the power of 4. Yes, to the power of 4. Okay, so that's going to be 3 is equal to u1 multiplied by 0.5 to the power of 4 is 0.0625. Okay, what we're going to do, we're going to divide both sides by this number over here. So it's going to be 3 divided by 0.0625 is equal to u1, right? This number divided by that is going to give us u1 is equal to 48. Yeah, let's double check that. Divided by 0.0625. It is 48 indeed. So we know now that u1 is equal to 48. So we have the common ratio, and we have u1 is equal to 48. Now I know that we have the common ratio for plus or minus, but that's just how it is. Yeah. So now we need to find u10. Well, u10 is equal to u1, which is 48, multiplied by 0.5, yeah, to the power of 10 minus 1, which is 9. Yeah. So this is the first equation for u10. u10 can also be 48 multiplied by negative 0.5 to the power of 9. Yeah, we have two possible sequences here, or we're talking about two possible sequences. Okay. Okay, cool. So this is going to give me 0.0937935, and this equation is going to give me negative 0.09375. Okay, so in this case, the sequence, our first sequence, we have two sequences here that we can imagine, just so we can understand the scenario. The first sequence is going to be 48, 24, 12, 6, 3, 1.5, 0.75, and so on. The second sequence is going to look something like this: 48, negative 24, 12, negative 6, 3, negative 1.5, and then 0.75. Now, if you look here at some of these terms, 48, our u1 and u1 are the same. And same thing for 0.75. Yeah, this is u7. 0.75 and 0.75 are the same. Also the same thing for u5, 3. They're both the same. So we can conclude that these answers are correct because it follows the pattern of these two sequences. Yeah, so it is correct. Okay, let's look at the sum of geometric sequences. Okay, so now moving on to the sum of geometric sequence. So the sum of a geometric sequence can be given by these two formulas over here. Okay, and in both formulas, of course, r cannot be 1 because we have 1 minus r or r minus 1 here. If r is 1 in any of those two cases, then the denominator is going to equal 0. And if the denominator is equal to 0, then whatever we're dividing by 0 is going to be undefined. We cannot have that whatsoever. Okay? So these are the two formulas. So now I'm going to do something that I haven't done this entire video, which is proving. Yeah, so I'm going to prove or show you how to prove these formulas, okay? So let's look at a geometric sequence by definition. If I want a geometric sequence by definition, well, what is that going to do? Or what is that going to look like? Well, I have u1, and then I'm adding another term, which I then multiply by the common ratio, right? Then the term after that is going to be u1 again multiplied by the common ratio squared, right? And then I'm going to have some things in between, and then it's going to go on and on and on until I get to u1 times r to the power of n minus 2. And then my last term of this sequence will be u1 times r to the power of n minus 1. It's not going to reach Sn. It's going to reach n minus 1. Okay? Now, the second sequence that I want to look at, or I'm going to write out, is r times Sn. So if I multiply this entire sequence by r, yeah, the common ratio, that means that my first term is not going to be u1 only, but it's going to be u1 times r. My second term is going to be u1 times r squared. And then my third term is going to be u1 times r cubed, for example. So wait, let me write that out. u1 times r cubed plus dot 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 plus, this case, u1 times is going to be u1 times r to the power of n minus 1. And the last term, instead of n minus 1, will be ur to the power of n. Okay? Because I'm going that further, I'm going one common ratio further, basically. I started with one common ratio later, so to say. I started with this term right here. Yeah? Okay. Cool. So now what I'm going to do is I'm going to take these two sequences and subtract them from each other. Specifically, I'm going to subtract this one here, which I'll call 2, and this one I'll call 1. I'm going to subtract sequence 2 from 1, okay? So 2 minus 1. So sequence 2 minus sequence 1. Okay, so sequence 2 minus sequence 1. Sequence 2 starts with r times Sn minus, and then Sn equals 2. Then all of this will be minus all of that, right? So u1 minus, so obviously we like for these for this sequence over here, yeah, it matches with this entire sequence as well. The only terms that stand out are in this case u1 and u1 times r to the power of n, okay? So the way that it's going to be then is that we're going to have this is going to be u1 times r to the power of n minus u1. And the reason it's like this is because every other term is going to cancel out. All of these are going to cancel out with each other. Yeah, this one too, and that one. Every single term is going to cancel out except for u1 because there's no u1 in the second sequence, and u1 times r to the power of n because there isn't a u1 times r to the power of n in the first sequence. So this is what we're going to be left with, okay? So from this side, I'm going to factor out Sn, yeah? So Sn multiplied by r minus 1, okay, equals 2. And then here it will be, I'll factor out u1. So u1 times r power of n minus 1, right? I then solve for Sn. So Sn is going to equal to u1 multiplied by r to the power of n minus 1 divided by r minus 1. And there you go. That is your formula proved. Okay? So that's that. Now we're going to move on and talk about the consecutive terms, and then we're going to talk about the sum of an infinite geometric sequence. Okay? So let's say I have my consecutive terms ax, b, yeah, in a geometric sequence. To find the common ratio, you multiply any term by the term before it. So you can divide. So you divide x by a, or you can divide b by x, right? So x divided by a is equal to b divided by x, which is equal to the common ratio. Okay, so that's something important to note. So that's number one. Number two, let's say that you have this middle term, but you don't have this middle term, but you have here this term and that term. So the term before it and the term after it. What can you do in order to find it? Well, I can say that I can divide this term by that term, so x divided by 10, right? And then equate it to, because it is equal to, 90 divided by x, right? So I said it, so this is my definition of, finding the common ratio with 3 consecutive terms. So since I have this, I can just solve for x, right? I can cross multiply. So I'll have x squared, right? And then 90 times 900, right? And then take the square root. That's going to be x equals plus or minus 30. Yes, and there is 2 solutions. There is in fact 2 solutions. That means that there are 2 geometric sequences in this case that we're envisioning, so to say. Okay, cool. So now moving on to the sum of infinite terms in a geometric sequence, okay? So imagine that I have the sum of infinity is equal to u1 plus u2 plus u3 and so on, yeah? So it never stops, okay? Now, it's given in the formula booklet, yeah? The sum of an infinite geometric sequence is given by u1 divided by 1 minus r, okay? For the value for when r, okay, is less than 1, okay? For when r is less than 1, okay? So this basically means that, or why is it like that? Let's see. So s of infinity is equal to u1 minus divided by 1 minus r, right? This series, we say that it converges, okay? But if r is greater than 1, then the series diverges, all right? So we need to prove these formulas as well, or why it is so, okay? So if I look at the first one, so let's look at the normal formula that we have, because we actually derive the infinite um, the sum of an infinite terms in a geometric sequence from the nth term formula, or the sum of nth terms in a geometric sequence formula. Yeah. So you have u1 multiplied by r to the power of n minus 1, all divided by r minus 1. Okay, sorry, let me just center that a bit. Okay, so r minus 1. Okay, so we're trying to find the sum of n terms, right? In this case scenario. Yeah. Now n, obviously the n terms in a geometric sequence that we're talking about are going to go on to infinitely. So we're gonna let n, yeah, let n go on to infinity. Okay. So if n is going on to infinity, so in this case it's going to be s infinity and u1 times r to the power of infinity, yeah. If r is to the power of n, yeah, then r is going to approach 0, yeah. If r power n, then it's going to approach 0, yeah. So in this case, for s infinity is going to equal to 0 minus u1, yeah, divided by, sorry, u1 divided by r minus 1, yeah? Because Rn is going to 0, is going to approach to 0, we're going to replace it with 0 minus u1 divided by r minus 1. This is going to be negative u1 is equal to r minus 1, and then with, like, so we can get rid of this negative sign, we can say u1 is equal to 1 minus r. Yeah, so you flip them around. So now you have u1 is equal to 1 minus r, and this is your formula. Yeah, s infinity is equal to u1 divided by 1 minus r. Okay, so now we're gonna look at a second way to prove the sum of a sum of infinite geometric sequence. Yeah, so the formula that we're trying to prove is u1 over 1 minus r. Yeah. So we're going to do it similarly to the one where we proved the sum of a finite sequence, which is like this. Yeah. We're going to do the same exact thing, except we're going to change our definition. We're not going to take just a classical geometric sequence. Yeah, a finite geometric sequence. We're going to look at a sequence that is infinite. Yeah, so it's going to be u1r plus u1r squared plus u1r cubed plus dot dot dot. Yeah, so it keeps going on and on. And then we multiply this sequence by the ratio. So instead of having, I made a mistake. Apologies. In the first sequence, it's going to be u1 plus u1 times r plus u1 r squared plus u1 r cubed. Yeah, and then that's going to keep going. In the second sequence, then it's going to just kick off right away with u1 times r plus u1 r squared plus u1 r cubed plus u1 r power 4 plus, and it will keep going. Okay? So now when you subtract both of these equations from each other, yeah, you'll say s minus rs is equal to, and then it's just going to be u1 because every other term is going to cancel out with each other, and it's going to go on infinitely. Those are all just going to cancel out. So you factor out s here, so you have s minus times 1 minus r is equal to u1. And then you're going to divide by this 1 minus r because you want s to be the subject. So it's going to be s is equal to u1 divided by 1 minus r. And there you have it. You proved your formula. Yeah. Okay, so that's that. Now let's move on. Okay, so now that we have geometric and arithmetic sequences down, we are going to actually look at their financial application because we can apply this to real world problems, for example, or real world situations. Yeah, let's say you put a sum of money in a savings account, for example. What is going to happen to that money? Yeah, how is it going to change? How can we calculate that? Yeah, so first of all, when we're dealing with problems like these, we're going to see something like this. So we're going to see R and then percentage sign. So this usually indicates some sort of rate. Yeah, so you can say an interest rate. Yeah, or it can also signal some sort of growth or decay, right? You can be, for example, population. Yeah, so you can be talking about population. So this is how, so you usually see that. And then we'll also usually be given something called a PV, which is the present value. The present value basically is the initial amount that you're starting with. So if I'm taking a sum of money and I'm going to put it into a savings account, then my present value is the exact sum of money that I have in this situation, and I'm putting in the exact money that I have right now. So if I'm putting 1,000 euros into a savings account, then my present value is 1,000 euros. Okay. And usually what we are trying to find is FV, which is the future value. Yeah. So after I put this money into a savings account, the interest rate is going to influence it. And however it influences it is going to be my future value. Okay? So that's that. So the formula is given by FV is equal to PV multiplied by 1 plus R divided by 100 to the power of n. Okay, so this is my financial application. And the thing is over here, this is an geometric sequence, yeah, because it's multiplied or it's to the power of n, yeah, and n in this case is my period, yeah. So how long I'm going to leave that money, or how long am I calculating this for, yeah. So there's two versions to this financial application formula. So it can be FV is equal to PV and then 1 plus R divided by 100 to the power of n. But it can also be FV divided by PV 1 minus R divided by 100 to the power of n. Yeah. In this case, here we are increasing. Yeah. The value of the future value is increasing. Here in this case, however, the future value is decreasing by percentage of R in a given time period, n. Yeah. So usually when you have questions like these, you're going to be allowed to use a calculator because it's much easier to apply it in a calculator. So you're going to have n is, let's say for example 10, so that's going to be 10 years. Then you're going to have a percentage that's given to you, so the interest rate or whatever it is. So you just put in the number. Yeah. So if in the question it's given to you that the interest rate is 8%, just put 8. Yeah. That's it. You don't need to do anything else. The calculator knows that it's in percentage. Then you're going to say PV, yeah, the present value. So if it's saying to you in the question that, for example, John puts $2,000 into a savings account, you're going to say negative $2,000. Now, why is it negative $2,000? It's because John is losing that $2,000. He's giving it away to that savings account. He's putting it into the savings account. So he's losing some of his money right now, okay? Because we're paying. He's paying for it, okay? Then you're gonna have PMT. Yeah, usually this is the payment like per month. Yeah, the monthly payment. So in this case, let's say it's just gonna be 0, and then you're gonna have FV. FV is not given. FV is usually what we're trying to find. Sometimes it's given in some situations, and we need to find another value. And then you're gonna have payment per year and compound per year, and usually these can just be left as 1. Sometimes a value is given to you. Okay. So then you're just going to simply go to FV and you're going to like click solve or yeah. So it's going to then give you some value for FV. Okay, cool. So we need to break down how this formula works. Okay, so if an amount increases by a percentage of R, yeah, we multiply by R equals to 1 plus R divided by 100. Yeah. So if a certain amount, like p value, is changing by interest R, we multiply it by this. Yeah, which is why we have 1 plus R over 100, right? And the reason that, let's say, for example, like let's say you put this for 1 year. Yeah, so it's just going to be this one. Yeah, this is going to calculate it for you for 1 year. You can know your present value from just this. But let's say I want to do it for 2 years. Then it's going to be PV times 1 plus R divided by 100 to the power of 2, right? This is going to be squared because you're going to do it for yet another year, right? And then what if it's for 3 years, 4 years, 5 years, 6 years, 50? I don't know. Yeah? Then in this case, it's going to be PV is equal times 1 times 1 plus R divided by 100 to the power of n years. Yeah, it's going to be any amount of years. Yeah. And that is how we find the future value. This is how we apply it to a financial account. Yeah. And again, just to make sure that we remember, um, for an increasing ratio, yeah, if R, like this one right here, the one I was talking about, this one, this is for when the value is supposed to be increasing. But for when it's decreasing, it's going to be R is equal to 1 minus R divided by 100. And this is what you multiply your p-value by. Okay? So that's that for the application of geometric sequences and so on.